Setting up hypothesis test. What can sample statistics tell us about the corresponding population parameters? So I'm going to use this example as to sort of introduce you to the language of hypothesis testing. We have a sample of n equal 100 patients. The proportion cured by a new drug, p hat, 75 over 100 or 0.75 or 75%. At the alpha equal 0.05 level of significance, will the cure rate of the new drug be higher in the long run than the 0.60 or 60% cure rate of the old drug? So I'm going to make a diagram here to kind of illustrate the relationship between the sample and the population. Setting up hypothesis test. What can sample statistics tell us about the corresponding population parameters? Example 1, in a sample of n equal 100 patients, the proportion cured by a new drug, p hat, 75 over 100 or 0.75 or 75%, at the alpha equal 0.05 level of significance, will the cure rate of the new drug be higher in the long run than the 0.60 or 60% cure rate of the old drug? So I'm going to make a diagram to show the relationship between the sample and the population. So we have a sample of n equal 100 patients. Proportion cured, p hat, 75 over 100 or 0.75 or 75% or cured. Okay, so this sample is taken from a larger population, and the population of millions of patients. Proportion cured in the long run by the new drug. It's represented by the letter P, and we don't know. So our best guess is that it's going to be 75%, because in our sample 75% were cured, but that might have happened just by chance. So we want to know what the sample tells us about the population. And so we want to compare it to the cure rate of the old drug. So that's known to be sometimes it's known to be 0.6. Sometimes you use P0 to represent the cure rate of the old drug, so to distinguish it from the P, which is unknown. So we're using the letter P in several different ways here. We have P hat, it's our sample proportion, and then we have an unknown population proportion, and we want to compare it to the cure rate of a new drug. Sometimes this is represented by P0 to distinguish this P from the population proportion. Okay, so that's sort of a diagram of what we're trying to figure out. So more formally, we want to test H naught P equals P0, it's H0 or H naught, P equals 0.6. The new drug is not better than the old drug, versus the alternative H1 or HA, P is greater than 0.6, the new drug is better than the old drug. Okay, so just a little bit about the terminology. The null hypothesis, H0, this is called the null hypothesis. That's that P is equal to 0.6. and the population proportion P is unknown, and the null value, that's the value of P if H naught is true, is going to be 0.6, the null value of P. And sometimes it's represented by P0. The other null value, that's the proportion not cured by the old drug, 1 minus P, or 1 minus 0.6, which is 0.4. The alternative hypothesis, so we have the null hypothesis and the null alternative hypothesis. Usually the alternative hypothesis is what we hope to prove. We're hoping that the new drug is better than the old drug. So we're hoping the evidence shows that the new drug is better. So it's represented by H1 or HA or H capital A. The Triola textbook uses H1. Other textbooks use HA. And the alternative either has a greater than symbol or a less than symbol. If it's less than symbol, that's called the left-tailed test. A greater than symbol, that's the right-tailed test. And a not equal to symbol, that's called a two-tailed test. In this example here, we only we're interested in proving is the new drug is better than the old. So this is a right-tailed test up here. So the this particular test that we're doing is a right-tailed test because that's what we're trying to prove. We're trying to prove that the new drug is better, that the cure rate is higher. The significance level alpha, I like to call it the level of doubt, but it's the official terminology is the level of significance. And we'll usually use 0.05. That's represent the probability of making what's called a type 1 error, which we'll get into, we'll explain a little bit more later. The confidence level, that's 1 minus alpha, so that's 1 minus 0.05, 0.95. So usually we'll use alpha 0.05 and confidence level 0.95. You may see some examples where you have alpha equal 0.01. If you want to be very, very careful about not making a type 1 error, you would have maybe pick a lower value for alpha. But the value of alpha is determined by the researcher. So it all depends on how confident you want to be in your conclusions. The sample size n, in this case, is 100. And the sample proportion p hat is p with a hat on. It's the x divided by n. X is the number cured in the sample, which would be 75, and our sample size is 100. So in this case, 75 over 100, or 0.75, whereas the percent would be 75%. The letter x in the numerator is, in this case, it's 75. This is the number cured. And it's what's called a binomial random variable. Bi because there are two possibilities: either the patient is cured or not cured. So that's and it's a random variable because the number cured can vary from one sample to another. So in this particular sample, 75 over 100 were cured. But if you took a different 100 patients, maybe only 60 out of 100 were cured, or maybe 80 out of 100 were cured. So it's random in that sense that the number cured can vary from one sample to another. Okay, so that's some of the terminology. In order to test the hypothesis, we want to check that n times p is at least 5 and n times q is at least 5. If that is the case, we can use the z-table as a shortcut for testing the hypotheses. Otherwise, we'll have to use tree diagrams, which I will get into later, or binomial probabilities to test the hypotheses. But I'll get into that in, I think, the third video. Okay, so n times p, so 100 times 75, p is 0.75 rather. 100 times 0.75 is 75. Is that greater than or equal to 5? And that's a yes. And n times q, 100, that's oh, I'm sorry, this should have been 0.6. I did p hat. 0. So that's the number cured if h naught is true. So 100 times 0.6, which is 60, which is greater than or equal to 5, and that's a yes. And n times q, 100 times 0.4, 40, that's also bigger than or equal to 5. So because we got yes, yes, then we can use this shortcut with the z-table. If not, then we'll, if you have yes, no, or no, yes, or no, no, then you would have to use the tree diagrams, which we'll get into later. And tree diagrams will give the exact binomial probabilities. If h naught is true, then this sample proportion p hat has mean or expected value the same as p, which is 0.6. So on the average, the sample proportion p hat will vary from one sample to another, but on the average, it should be agree with the population proportion, which, if h naught is true, would be 0.6. And the standard deviation given by this formula here, square root of p times q over n, square root of 0.6 times 0.4 over 100. And we can put this into a calculator. And we can do it all in one step on the calculator. The calculator knows something about the order of operation. So if you do second x squared, that brings up the square root function, and then 0.6 times 0.4 divided by 100. And as long as you don't push equals on till the end, then the calculator knows a little bit about the order of operation. So this is 0.04 8989 795. Okay, so I'm going to store that in memory so I don't have to retype it later. Store it in memory on my calculator. Okay, so then we can compute this test statistic. This is the z-score. You might recall from earlier in the course, the z-score is the score minus the mean divided by standard deviation. In this case, we're using the mean of p hat and the standard deviation of p hat. So it's p hat minus the mean of p hat divided by standard deviation. So it's p hat, the mean of p hat is p, standard deviation square root of pq over n, which we already computed. So we already partially did this computation. So z is going to be p hat minus p, so it's 0.75 minus 0.6, and divided by 0.048989795. And so the calculator does not know about the long division bar. The short division symbol, if you see the short division symbol, that has precedence over subtraction. But a long division bar that goes all the way across comes after the subtraction. So that our calculator doesn't know about the long division bar. So we're going to have to force it to do the subtraction first. So you do the 0.75 minus the 0.6 and then push equals to force it to do the subtraction first. In fact, I'll write out that step here. It's 0.75 minus 0.6, 0.15, and then you want to divide by this number here, which I stored in memory, so I can just pull that up from memory on my calculator. So, 0.75 minus 0.6, and then push equals. That gives the 0.15, and then divide by second recall. Equals, and it's approximately 3.06. 0.06. So that's our test statistic. Okay, so the next step is to go to the z-table, but because we have a right-tailed test and we're using a left-tailed table, we need to look up the opposite sign. So we want what we want is the probability. So this is called the p-value, and for a right-tailed test, is going to be have a greater than symbol. So we want the probability that z is greater than 3.06. So that's the right tail. The picture looks something like this. You know, what the probability on the right side, the probability corresponds to the area under the curve here. But our table is a left-tailed table that has the probability of z being less than a number. So we want to change the sign. The probability of z less than negative 3.06. So that's the left tail. These are based on the bell curve, which is symmetric. The left tail has the same probabilities as the right tail. And then, so we want to go to row negative 3.0 and column 6 of the z table. So row negative 3.0 and then go across to column 6, and we get the probability of 0.0015. 00.11 rather, 0.0011. So that's our p-value. And that is less than alpha. So the p-value of 0.0011 is less than alpha, which is 0.05. And sometimes it helps to add some extra zeros, so that makes it easier to compare the numbers. So if we add extra zeros here, we'll have the same number of digits after the decimal point. So 11 is less than 500. 0.0011 is less than 0.05, but it's more obvious if you add the trailing zeros to have the same number of digits, and then just compare what comes after the zeros. 11 is less than 500, so that means the p-value is less than alpha. So that means we reject H naught with 95% confidence. And conclude the new drug is better than the old drug. Okay, there's a shortcut actually, even without going to the table. This is using Triola's range rule of thumb part 2. For a right-tailed test at the alpha equal 0.05 level of significance, any test statistic more than 2 will provide sufficient evidence to reject H naught. This shortcut is not as accurate as the p-value method, but 3.06 is more than 2, so that means we fail to reject we reject H naught. Reject H naught and conclude new drug is better. So that's a kind of a shortcut. You can also use it as a check. So if the exact method and the shortcut don't agree, you that might be a clue to go and check your work to make sure you did everything correctly. But this is not as accurate as the p-value method. Another comment here: if we want to lower our chance of what's called a type 1 error, which I'll get into shortly, that's the probability of rejecting H naught when H naught is true. We can compare the p-value to, we could change our value of alpha. So we compare our p-value to alpha equal 0.01 or 0.001. So the level of alpha is kind of arbitrary. It's determined by the researcher. It all depends on how much of a chance you want to make of making a type 1 error. Another comment: technically we never accept H naught because it might be that a larger sample would provide stronger evidence against H naught. So technically we either reject H naught or we don't know. Now some researchers simply report a p-value, and this chart can help with interpretation of p-values. P-value equal to 1, that means there's no evidence against H naught. P-value between 0.1 and 1, little evidence. Between 0.05 and 0.1, some evidence, and so forth. Again, it might help to add trailing zeros, because our p-value had 4 digits to the right of the decimal, so it'll help for comparison purposes if we add trailing zeros. So if I add 3 zeros here, we'll have 4 digits to the right of the decimal. 1, 2, 3. And then 2 zeros here, we'll have 4 digits to the right. 2 zeros there, 2. Only 1 zero here. Oh, 1, 2, no, I had 2 zeros there. Okay. Okay, so our p-value is 0.0 0.0011. So the last, if you look at the number after the trailing zeros, we have 11. So 11 is between 10 and 100. So that means it's strong evidence. So it would be this one here, strong evidence. Gives p-value of 0.00, gives strong evidence against H naught. So strong evidence the new drug is better. Because 0.0011 is between 0.0010 and 0.0100. So 11 is between 10 and 100. So that gives strong evidence that the new drug is better. Okay. Okay, so I mentioned, I'll say a little bit more about alpha. I'm going to make another diagram here showing the possible outcomes of hypothesis testing. So either H naught is true or H1 is true. And either we reject H naught or we don't reject H naught. Okay, so we have 4 possibilities. H naught could be true and we don't reject H naught. H naught is true and we reject H naught. H1 is true and we don't reject H naught. H1 is true and we reject H naught. Technically, we never accept H naught. Either we reject H naught or we don't know. Okay, so the probability that we don't reject H naught, if H naught is true, is called the confidence level. That's 1 minus alpha. And the probability that we reject H naught, if H naught is true, that's called a type 1 error. Probably we don't reject H naught if H1 is true. That's the Greek letter beta. Looks like a B. And that's called a type 2 error. And probably reject H naught if H1 is true. That's 1 minus beta, and that's called the power. Okay, so 1 minus alpha, that's our confidence level. Alpha, desired level of significance. I like to call it the level of doubt. It's probability of a type 1 error. p-value. I put here actual level of doubt, but actually it's more precisely it's the probability of getting a result this extreme if h0 is true. Greek letter, and it's the number that we compare to alpha to decide whether to reject h0 or not. Beta, the Greek letter beta, looks like a script B, capital B, probability of a type 2 error. It's the probability we don't reject h0 if h1 is true. And 1 minus beta, that's called the power of the test. So so we have 4 possible outcomes, and 2 of them are errors, 2 of them are correct conclusions. So the 2 errors, reject h0 if h0 is true, or don't reject h0 if h1 is true. Okay, so some exercises. Is it possible we made a type 1 error in example 1? So in example 1, we rejected h0. Okay, so if we reject h0, then you take a chance of making a type 1 error. Okay, if we reject h0 and h0 is true, that's a type 1 error. If we reject h0 and h1 is true, that's not an error. But, so the answer is yes, because we rejected h0. Is it possible we made a type 2 error in example 1? And no, type 2 error can only happen if you don't reject h0. So no, because we rejected h0. If in example 1 alpha is 0.001 instead of 0.05, what type of error might we have made? So the p-value was of 0.0011 is more than this new value of alpha, which is 0.001, and it may be helpful to add an extra 0 here to make it obvious. 11 is more than 10, so that means 0.0011 is more than 0.001. So that means we would fail to reject an h0. That means there's not enough evidence. It doesn't mean that h0 is true. It just means there's not enough evidence to reject h0. So if we fail to reject h0, then it's possible we made a type 2 error. So either way, you make it. There's always a chance of making some kind of error. So if you reject h0, you might be making a type 1 error. If you don't reject h0, you might be making a type 2 error. And the best way to lower the chance of either type of error is to increase the sample size, but the drawback there is that larger samples are more expensive. And that concludes this presentation.